Alright, so let's see some of this polynomial solving in action here. Let's look at this first got it problem up here in the upper right. Notice the difference between in these kinds of questions that they're actually asking you for. Notice they're asking you for not only the real solutions, but they're also asking you for the imaginary solutions too. Very interesting. Okay, so see how that slight little change in the question will kind of force our hand to come up with a couple more answers than just the real ones. So what do you notice about this problem? It's already factored. Okay, now I could really see two different routes you can take with this. You could continue to factor that x squared minus 1, because quite honestly it's one of these guys right down here, which is the difference of two perfect squares. So we could look at that guy right there, factor that as x plus 1 times x minus 1, but there's no such thing as a sum of two squares. So you'd have x squared plus 4 equals 0. Then we'd have to use the zero product property, which would tell us that three things, right? That x plus 1 could be equal to 0, that x minus 1 could be equal to 0, or x squared plus 4 could be equal to 0. And so solving each one of these, subtract 1, subtract 1. Here's one answer, x equals uno. Here's the other answer, add 1, add 1. So, oops, I'm sorry, back here. That should be negative 1, shouldn't it? Yep. Glad I caught that. And then adding the ones here, x should be a positive 1. And then over here, solve this algebraically by subtracting 4. X squared, not x, is equal to a negative 4. And then when you take a square root on both sides, realize you're taking a square root of negative 4, and there's that imaginary unit about to pop up, right? So the square root of 4 would be I, but then we also have the 4 there, but also keep in mind we're taking a square root to solve. So we have two answers there, plus and minus for I. Okay? This will be one of the first of many times you'll hear me talk about the fundamental theorem of algebra that we will cover in section 5.6. And if you were to actually multiply these two together, x squared times x squared, and actually FOIL it, the degree of the polynomial will be x to the fourth. And a corollary to the fundamental theorem of algebra states that whatever the degree of the polynomial, that's how many complex solutions you have. So you count them up. We've got 1, we've got 2, we have actually 3 and 4 solutions right there when you count the plus and minus, right? So that fits with that fundamental theorem of algebra, which we'll dig into completely when we get into 5-6. Now, the reason why I put a break right here is that I could see another way of solving this problem. Couldn't you really solve this problem just using the zero product property right now? We used it right here after we factor the difference of two squares. We could have done it right here too, right? We could have said x squared minus 1 could be 0, or x squared plus 4 equals 0, and then solved, just remember how we solved this one algebraically by subtracting 4, and ending up with x squared equals negative 4, and then ultimately ending up with not just 4i, but positive and negative 4i. We could do the exact same thing here, right? Couldn't we add 1 to both sides? Set us up with x squared equals 1, and then when we take the square root to isolate the x, remember we're taking a square root when you solve, there's two answers, a positive and a negative case. In this case it's 1, so then 1, 2, 3, 4. Remember, fundamental theorem of algebra, 4 solutions. Okay, so the last thing I'll look at right here on this page is just going through and reviewing some of those factoring techniques that you did in quadratics in chapter 4. You did factoring out GCFs with quadratics. This also works for polynomials. Just look for occasionally, sometimes that greatest common factor might not just be just the number, and it might not just be x. Sometimes it could be a larger degree of x, in this case x squared. Okay, quadratic trinomials, we talked about the real simple kind. This is that really ugly one where you have a leading coefficient that's not 1, and there are no GCFs here. So either guessing or checking or factoring that by grouping. In fact, they talk about factoring by grouping right down here, right? These are the ones, think back to chapter 4, where I made you put brackets, not parentheses around there. And we factored this by taking out GCFs in each one. So if I were to take out the GCF in this guy, GCF would be x squared. We'd be left with x plus 2. take out the GCF on this one, we could factor out a negative 3, and that would leave us with x plus 2. Remember that road sign that says we're on the right track? There it is. Those doubles. Write that down, because that's a GCF of those two factors. And then what we didn't have, which was the x squared and the negative and the minus 3 that we didn't have in parentheses, there's your other factor. Okay? The only one that's really new here is that sum and difference of cubes. Common question I did get from Accelerated Algebra 2 is there a need for both of these? Well, yeah. Do you see a difference if you run across, say, a sum of two cubes like 8x cubed plus 1 versus a difference of cubes? See how they get factored differently. Okay? So to briefly talk about this, what's the connection between this guy and that guy? Well, quite honestly, it is really the cube root here. Can you think of something that when you take it and raise it to the third power, you get that value right there of 8x to the third? Okay, we'll look at an example here in the textbook here in a second, because sometimes this might be a little bit tricky to explain. So how about I set that up for us right now? So let's take a look at number 11. I think I assigned this problem in your homework. And this has a very distinctive look here, x cubed minus 1,000. Do you see which one it fits here? Definitely not a sum of two cubes, but definitely a difference of two cubes. So let's take a look at how this goes down. Your first factor portion of this difference of two cubes is the cube root of each one of those two terms in that binomial. So factor this one properly. Your first move, cube root of x to the third. I think that's x times x times x, so we can write down x. And then the cube root of 1,000. Can you think of a number that when you multiply it by itself 3 times you get 1,000? I think you can do that with 10. 10 times 10 times 10. So based off of this little template right here, see that minus sign? We're going to put a minus sign right there. Here's a part that gives students a lot of trouble. A lot of students want to keep looking here to figure out what goes into those 3 spots right there. That's a bad place to look. Instead, great place to look to figure out what goes there would be what you have here and here. Because what they're trying to tell you here, here, and here is all this stuff is based off of what you get there for a and b. So let me show it to you. See how this one just says a squared? Then when you just take whatever a is, square it. So what is a in this case? It's x, isn't it? So we're going to write in x squared, followed by a plus sign. What they're trying to tell you with a and b, take the two isolated terms right here, the x and the 10, multiply those together, so now I'd have 10x. And then last it says b squared, so whatever b was, in this case b was 10, you square that 10, boom, there's 100. Now I've got some good news and I've got some bad news about where to go from here. Do you notice the directions? It's asking you to find the real and imaginary solutions. See, there's that equals 0 right there, which I'll put that in there. Here's the good news. One of the zeros, when you do a difference of two squares, pretty easy to spot. And that's this guy right here, right? You're used to seeing this guy. So, based off of that, we have this guy times this guy right here. And if both of those two things multiply together to give you 0, what must be true is that x minus 10 could be 0, and that leads us to one answer of x equals 10. Boom. There's one out of the 3 answers that we have. We're going to have one real answer, and we're going to have 2 imaginary answers. Now, how do you know there's 2 imaginary answers? Well, take a look at this here. A couple things I could tell you about why that's imaginary. Number 1, first, you can't give me any 2 numbers that are real that can multiply it to 100 and then still add up to 10. So in other words, that first factoring move of factoring a trinomial, impossible to do. So that's the bad news about sum and difference of cubes, is that it's impossible to factor it. That trinomial right there. You can never do it. Okay? But turn that into some good news. Turn that into some information that says, well, since I can't factor it, the only other way I can find a solution or find out when x squared plus 10x plus 100 is equal to 0 is a very, very familiar and very, very easy to use formula. You betcha, there it is right there, the quadratic formula. So then you can take stock on A, which is 1, B, 10, C, 100, and let's go ahead and substitute those numbers in there. I'll pause, save some time. Alright, so take a look at that. Did I substitute everything in there properly? Think so. So then your next move, just worry about what b squared minus 4ac is. That's how I knew it was imaginary, because if you do that, you're going to get 100 minus 400, right? And if you do 100 minus 400, you're going to end up in negative zone, And sure enough, we're going to have the square root of negative 300 divided by 2. I can go ahead and multiply those together. No harm, no foul there. Okay. So which brings us to our next move, which is simplifying that square root, that negative square root. Takes a little bit of thinking, but I think you got it. We'll keep the negative 10 right there. All we have to do is factor out that negative 1, and then really think. We take that negative 1 out of there, we're staring at 300. Can you think of a big perfect square that can go into 300? I can think of one. I can think of one. I could think of 100. Yeah, 100 can go in there 3 times. Okay, put a box around that 100 to remind yourself to take the perfect square root. Same thing with that negative 1. Boy, we're writing a lot here. But yeah, sometimes this takes a little bit of extra elbow grease to get the right answer. We're okay. Negative 10 plus minus square root of 100. There's a 10, square root of negative 1, which would be your I, and then square root 3. Next move, reducing that fraction. Bing, bang, boom. I can reduce that fraction. And so now I'd have negative 10 divided by 2, which would give us negative 5 plus minus. And then we'd have 5i times the square root of 3. Shoo! So now I got a couple more answers to add to that right underneath that 10. Let's put them right up here. So 2 more answers here. Not only could x be 10, but x could be negative 5 plus 5i square roots of 3. The last one here, negative 5 minus 5i square roots of 3. Okay, so there's 3 answers there for us. 3 solutions. We found the real one, we found the 2 imaginary ones. Outstanding. So that's kind of how in this case, what was this one? A difference of 2 cubes is worked. Sum of 2 cubes, really not a whole lot that's different about it. Just note the thing that's different is that how you start that factor job right up there. And see the subtle difference there. Like I like to point out to students here. Look at that first part right there. See how plus, plus, minus, minus. And then if this is a plus right there, see how the plus is here and then the minus is there. And then same sitch right here, but just the reverse. A minus there and a plus there. Okay? That's how those work.